But this is wrapping Amazon. You guys streaming?
Yep, streaming now.
So streaming. Cool. So I can start?
Yeah, we're live.
Hello, everyone. So nice to see you guys. I'm here to talk about making robots think faster, and I'm just going to be giving an introduction to hardware acceleration, talk a bit about what I do, how you can get into it, how you can do it well. So just out of curiosity, what years is everyone in? Is anyone in second year of second year? Third. That's cool. Got a pretty decent spread here, actually. Yeah, so oh, just a second one. How many of you guys haven't done CSSE 2010? Cool. Good to know. All right, so I will introduce myself because I see a lot of new faces. Don't recognize a lot of people anymore. So about me, I'm Raghav, but people generally call me Raggy here. And I graduated from my BE-ME in 2021 doing mechatronics. And nowadays I work as a robotics engineer at Amazon. I like a variety of things, but my main interests are around control theory, motion planning, state estimation, things of that nature. And I've tutored a bunch of related things at UQ. So if you're doing mechatronics for electrical, you'll probably do some of the courses I used to tutor. So 4202, 4201, 6203, and Elect 3004. And just, I'm not here representing my employer here, but I do want to give some context for what kind of problems we face as a robotics company. So to give some background, I work at Amazon, and we're one of the probably one of the larger robotics companies in Australia. Our main product is that little thing over there. So that thing under the drone there is what we call a hover map, and it's what we call a robot payload or scanning payload. What it actually is effectively this chassis with what's a motor, LiDAR sensor, so the kind of sensor that you would see in a self-driving car and nowadays on iPhones for some reason. Yes, it's got a small computer inside, some bunch of compute, and what it actually does is sort of takes over and hijacks the brain of whatever robot platform we're connected to. So here we've got a drone, and most of our clients are drone users. But you can also use the payload on its own. So you can turn it on, connect it to your power, and turn it on, and it'll start scanning and work on its own without any robot. We do also support Boston Dynamics spot robots. So that's what you see on the right, and we're doing some trials with a bunch of customers here and there on commercializing that technology. And whatever robot you connect to, the interface that you see is on the right here is what customers see. So effectively, as the robot gets taken over, we are able to use the laser scanner there to make a 3D reconstruction of the environment around us, and use that to navigate, use it to visualize what's going on, and things of that nature. And this middle photo here is just our work with CSIRO. So we are, as a startup, we launched in 2018. And we actually spun out of CSIRO's robotics group, and we took part in some interesting challenges. So that's the DARPA Sub-T challenge, where we got second place, beating MIT, Caltech, and a bunch of other big names. So yeah, we have some very cool tech, but I don't think I think there's still a bit of a question mark on what this is for. Like, what are these robots for? And that's what the next slide here I have is for. And so as LiDAR payload actually uses the LiDAR sensor to create these high quality 3D maps. And so these are not artistic renditions. These are actual scans we've done with all of the detail. The ones on the left and the top there are just laser scans that have been colorized with just for good visualization. This one's actually been colorized with an actual camera. So we run the LiDAR scanner with a GoPro, and then we use the GoPro footage to colorize the points so you can actually visualize it. But these are all just high fidelity scans of that our payload has taken to help customers do inspection, surveying, and mapping. So customers might have some sort of bridge that they want to inspect, or they might have a mine site they want to explore, or they might have a cultural heritage site that they want to be able to, say for example, keep and like send information about to other people, or a variety of different things that can be done with a high fidelity 3D map. So that brings to question, how do robots think and perceive the world? And why do they need to be fast at it, right? So my talk is about hardware acceleration, so I need to justify why stuff needs to be accelerated. So depending on what kind of robot you have, you might be doing different things. You might have different sensors, different information. So what we primarily use is LiDAR, and that's not our LiDAR, that's some self-driving car companies' LiDAR, but you can sort of say with LiDAR, what you actually have is a laser sensor where you've got like 16 to 128 lasers in a row, and sort of send pulses, small pulses, and then count how long it takes for them to get back, and that gives you a measurement of how far away something is. And so when you take these 16 to 128 lasers, and you constantly blast out pulses to measure how far something is, and then you spin it, you get these rings, characteristic rings, telling you how far something is. And this is sort of a one snapshot of what they're measuring. But you can hold this information and use it to create high quality maps like we do. Something that we don't currently use, but other types of robots might want to, like for example, robots with arms, or robots operating in day-to-day house environments, is cameras. Cameras are very cheap sensors that are able to give pretty high quality and high quality information that other sensors might not be able to. So here is a camera being used to create, it's got some RGB information, and it's being used to estimate how far away something is and what it is. So whether it's a wall or a room or something like that. And then on the right is the reconstruction that you're seeing happening live from the camera. And so both of these sensor technologies take quite a lot of computation, right? So with LiDARs, you've got a lot of information coming in. With cameras, you have to do a lot of processing. So here what you'll have is not just this 3D reconstruction process, but you'll also have neural networks to figure out what the semantic label there is, so like guessing what each pixel is. And they might also want to do post-processing. So if you've got a bunch of data off a map, you might, for example, want to create this thing called a distance field. This distance field is able to help you in making plans about what to do and doing collision avoidance and things like that. And robots also need power efficiency. Now, I don't know about every robot, but our robots are constantly flying, and it's generally a bad thing if like 10 kg robots fall out of the sky, and flight times are somewhere between 20 to 40 minutes, depending on what kind of drone you have and what you're doing. And we want to extend that as much as possible, both for safety and just for capability reasons. So how fast do we really need to think? Well, here's our latest product, the HoverMap SDX. That's the latest payload. And on the maximum, it can return up to 2 million points per second. And that's just raw sensor information. All of these points not only need to be processed once, they need to be used to create reconstruction, do these reconstructions online while the robot is running, and then use this information to plan where to go and how to avoid obstacles and yada, yada, yada. And so there's a lot of data coming in. Here's another example. This is not our robots. I am not allowed to give you out the details of everything. But here's a drone stack that's open source from the University of Pennsylvania, and it sort of tells you the rates at which different parts of the robot are doing things. So you might have inertial measurement units, stereo cameras, LiDAR sensors, and so those are sort of in the range of LiDAR's 10 hertz there, stereo cameras 30 hertz, IMU's 200 hertz, and that's the information. That's the rate at which the information is coming in. And then all of this is the right-hand side is sort of the thinking processes. So mapping and estimation are sort of using this using the information to figure out where the robot is and what's around it. Planning is figuring out what to do. Control is figuring out how to do it and just actually doing it. And then this is the actual physical robot. And you'll see depending on what you're looking at, the range is from around 1 hertz, which can be like the slowest I want to go home type of planning, to 10 hertz, which is sort of what path I need to take home to move around, to sort of different things. 200 hertz control, which is what motor speeds do I need to what motor speeds do I need to be pulling to not crash into stuff. And so there's depending on which part of the stack you're in, you might need to do things at different rates. So for example, if you need to do something at 100 hertz rates, that means that thing, if you do 1 on 100, that's 0.01 seconds. That's how long you have to get all of the processing done. And they'll depend on different parts of the stack. Sometimes it might make sense to not do hardware acceleration because it's just a very slow process. Other times it might make sense because you need to get done really fast. But what is hardware acceleration? Well, hardware acceleration is the process of using specialized hardware to speed up your computational algorithms. So I've sort of I've adapted this format of this general purpose and flexible to specialized and efficient spectrum. And almost every one of us spends almost all of their time on this side. Everyone is using normal CPUs and just doing general purpose computation, right? CPUs are very general purpose machines. And then I've sort of laid them out like this. Right next to the CPU is still a CPU, but using specialized instructions. Graphics processing unit, a field programmable gate array, a variety of different specialized hardware types, and then even more specialized custom hardware that you might have. And I'm just going to explain why this particular list. But so CPU is a general purpose machine with very general purpose instructions, but it has available to specialized instructions for you to be able to do fast tasks. So for example, you might have SIMD instructions, which are single input multiple data instructions, which are basically you can operate in many things at once. A GPU is what we've probably seen a lot. If we're gamers, we use GPUs or graphics processing units to do a lot of graphics and rendering type work for gaming. It turns out that they're made for graphics and have traditionally been used for graphics, but they are very general. You can sort of do a lot of different things on them. A bit more specialized is FPGAs. Now, an FPGA is sort of a very general purpose thing. You can use it for anything, but what you'll do is you specialize it for your particular task. So an FPGA is actually sort of programmable hardware. So you're not writing software for it. You're writing a hardware configuration that makes it rearrange itself in a particular way such that it acts like specialized hardware. Then on the right-hand side, you've got non-configurable hardware. So either you're buying a chip specialized for a particular purpose, and I've given examples there. So a tensor processing unit for machine learning, DSP for things like audio, etc. Or if you've got loads of money, which most robotic companies don't, but some do. So for example, Waymo, which is Google's self-driving car division, and Tesla, they have specialized divisions that work on robotic-specific chips for machine learning and for other types of inference happening on a robot. And so those are ASICs, application-specific integrated circuits. At this, you almost certainly won't have to go past this line for most robotics situations. If you've got a special situation, you might want to go till here. If you've got some machine learning happening or something, you might use some of these. And if you've got loads of money like Tesla and Waymo, you might be here. Now, there's a variety of things we might want to accelerate within robotics. The robotics tends to follow this sort of perception, planning, and control categorization of things we do. I vaguely grouped them into it. We can split hair about what's what, but on the left-hand side, closest to the actual sensors, is sensor data processing, vision algorithms, point cloud algorithms, simultaneous localization and mapping, which is figuring out a map of what's around you, machine and deep learning. Then a bit more on the planning side is stuff like occupancy grids and distance field, and that's what I showed you before with the weird slicing image, kinematics and reinforcement learning and collision detection and all of these planning things. And then on the control side, we generally don't tend to do that much hardware acceleration on the control side, except maybe at the motor level. But yeah, so that stuff can happen. I know self-driving cars do use probabilistic trajectory generation algorithms and things like that. Generally, we tend to do hardware acceleration most on perception, a little bit on planning, and generally the least on control. So how do I actually use hardware acceleration to speed up my robots? Right? Well, the theory behind it is you've got happening over time a bunch of different tasks, and then it gets to this really computationally heavy task. It might be processing the latest batch of sensor information, so it tends to come up in big packets of information, and then you have to go back to other tasks, and you sort of have to speed this up. And the theory behind it is that you make it take a lot less time in exchange for some sort of extra time it might take to send the data over to external hardware and then spin up some code, right? So on the dedicated hardware itself, it takes less time, but you still have to worry about this extra piece of time. And once you've done that, the CPU is actually free to do other stuff if you wanted to do other stuff. And obviously, because you've saved all this extra time, you actually have all of this extra time here too. So how do you go from this computationally heavy algorithm taking all of this time to this amount of time? Well, it sort of depends, but the main general idea is taking advantage of two things: problem structure and hardware specialization, right? And those are the two key things. You try and take advantage of the structure of your problem to break it down into things that can be done faster. And then you take advantage of the what your hardware is efficient at to do it in less time. And the main idea is actually parallelization. And that's for like 90% of hardware acceleration, it's about parallelization. What I mean is that a CPU is like this massive Pac-Man here, right? It has a stream of tasks to do, a bunch of instructions to run, a bunch of algorithms to do, a bunch of data to look through. And it does them in very fast in a serial manner. First it gets through A, then it gets through B, C, D, etc. Right? It's very linear, but what hardware accelerators really excel at is they might not have a big Pac-Man, they might have a bunch of smaller Pac-Mans. And if your problem has a structure where you can sort of split it up into smaller different tasks, then it can be extremely efficient. So even if it takes one Pac-Man less time to get through one of these boxes, it's more efficient if you can have 4 of these, do all of them at the same time, right? Significantly more efficient, in fact. And this sort of relies on the idea that all of your tasks can be parallelized in such a way, right? So it might not be the case. So for example, if the C box, right, if processing the C task depends on your on the answer for the A task, then the best you can do is you can do maybe A, B, and D, and then you need to wait until those are done, and then you do C. So you're sort of relying on a problem structure to fit your hardware. So the most common pattern you'll see for hardware acceleration is the map pattern. What I mean by that is that you have a bunch of input data, those green boxes on the top, and you can, without any sort of communication, take all of them and then apply some operation on them independent of every other input data, and then get that output, right? You're mapping this input data by some function, by some process. And that might be pretty useful. So for example, if you're trying to, say, add two vectors, right? For each dimension of that vector, you can actually just add those two independent of all the other dimensions, and you'll just get your output. Another common one is reduction. A reduced pattern is sort of, the last one was sort of multiple input, multiple output, right? And all of the inputs were independent of each other. This is sort of a multiple input, single output, where what I mean is you are doing this sort of reduction into one single output. So you might wonder why you might want to do it like this. It's a pretty crazy tree-looking structure. And my answer is a lot of common things that we do to fit this pattern. So for example, I give the example of adding two vectors together, right? Imagine if we're not trying to add two vectors together, but adding up all of the values in a single vector, right? And what you might be able to do, well, if you're on a CPU, you might make a for loop, right? A for loop that goes through 0, 1, 2, 3, 4, and it basically takes a sum output. You've got a sum variable, and then you keep adding to the sum as you iterate over this vector. In a reduced pattern, instead of going through this serially, you can take advantage of the associativity of the addition operation and say, maybe one part of your processor will add 0 and 1 together, right? Maybe another part of your processor will add 2 and 3 together, and so on and so on. And the benefit there is that you're having all of these operations happen in parallel, and then you can actually take these outputs and then add those together. So the 0 plus 1 added with 2 and 3 can be added together later, right? So here, you're adding the 0, 1, 2, and 3 together. And then as it goes down to this end part, you'll have a sum of everything. And I will note, this is actually taking advantage of the fact that the sum of A plus B plus C is the same. Well, actually, it doesn't really work in audio. A brackets B plus B and close bracket, and then plus C is the same as if you move the brackets around. It doesn't work in every operation, and so you sort of have to be careful there. It might not work for subtraction, for example, depending on how you do your brackets. But it does work for a lot of things. So if you can imagine multiplication, right? You can multiply all of these. And some ones you don't expect, like max, right? The max of A, B, and C is the same as the max of A and B, maxed with that and C. And if you move around, the maxes works the same. So reduction is also a very common pattern and tends to be quite useful. Oh, and there, mind you, I only introduced 2 of these. There are a bunch of different parallel programming patterns that are quite common. And in fact, a lot of the time you can, if you don't know how to parallelize your algorithm, just look through a list of these patterns, and you'll probably figure out a good way if there is a good way. So GPUs, and a lot of us are actually used to the idea of GPUs. A lot of us are gamers or joined engineering because they wanted to make GPUs and stuff, I hope. That's why I joined engineering. I now use GPUs, which is not the same thing, but close enough. So the GPU programming landscape is actually quite rich compared to some other hardware accelerators. We've got a lot of different options, almost spoiled by them. The most common is CUDA, and I know someone was struggling with CUDA literally today here. AMD has their own copy of CUDA. The platform is called ROCm. The language itself is called HIP. I think it might be the other way around. It looks exactly like CUDA, so this is bizarre. OpenCL looks similar, but it is an open it's an open ecosystem. So with OpenCL, you can actually use OpenCL on NVIDIA, Intel, AMD, and also you can use them on FPGAs and a bunch of mobile processors and things like that. So it is quite an open ecosystem. It's an inferior ecosystem, but that's a separate thing. OpenCL is quite old now. And for context, all of these above this SYCL here they're actually sort of C-based programming languages. So they're basically small modifications onto C to support this sort of parallel processing and maths type stuff. SYCL here is the odd one out. It's a quite recent one. In fact, there's still only a couple implementations of it, but it is supposed to be the successor to OpenCL. So the same people that made OpenCL are formalizing SYCL. There's a big implementation by Intel, and yeah, it's looking very promising. SYCL is actually based on C++. It's able to be a lot more flexible and powerful in terms of programming itself, simply because it's C++. Give me 2 seconds. So, CPU versus GPU architecture. So I sort of talked about this with the Pac-Man analogy, but with the CPU, what you have is a bunch of RAM, right? And inside the CPU itself, you've got some sort of cache memory, which is like high-speed memory that you have access to. You've got a bunch of ALUs, and if you do 2010, you sort of like vaguely understand these concepts. But effectively, ALUs do your math operations. Control units control the ALU to control the flow and execution of code. Cache is your sort of like very quick memory to access, and RAM is sort of your largest storage for your CPU. So when you want to do operations on some data, your processor will grab data from the RAM. It'll apply operations with the ALU. It'll make these temporary these temporary storage in the cache, and all of that will be controlled by the control unit. A GPU is vaguely similar, but with very, very different ratios of things. So it has access, it still has a RAM, but it has loads of ALUs, way more. And they all share the same execution unit and the same cache. And so you'll have actually these massive blocks of just pure processing machines that can do loads of things at the same time, but they are controlled by the same execution unit. So here's a glossary, and it's going to get real confusing if you're not used to this. But there's a few very weird words there. In GPU glossary, you launch kernels. Kernels are some sort of parallelized piece of code. So you might have a kernel to process some data. You might have kernels to process some image or do some computation of some kind to perceive, plan, or control. These kernels have, at the lowest level, threads, and they are in a sense exactly the same as CPU threads. A thread is a single a line of execution. So each thread is processing on some piece of data, just that single piece of data at a time, and there's multiple threads happening in parallel. So if you've heard of multi-threaded programming, that's sort of the same sense of threads. These threads are usually grouped into some sort of, in OpenCL terminology, it's groups. Confusingly, in CUDA, they're called blocks, which I do not like. So these blocks sort of operate together. These blocks will share the same execution unit as they're doing computation, and they'll sort of like follow the same logic at the same time. And we'll talk about that in a second there. And threads in a group will share some sort of local memory. So what that means is if you've got all of these threads operating together, they actually have access to some of the same memory, so they can actually share some information. And all the groups can access global memory, which is the memory of the GPU. So like on a GPU that's VRAM, if you got an integrated GPU, that's going to be the same as RAM. And yeah, just take a second to digest this, because otherwise it can get confusing. I know it took me I had to remind myself again and again what was what when I first started getting into it. Cool. So here's an example from CUDA. And just for context, I've literally randomly thrown around examples from different ecosystems and different hardware and different software platforms. They look mostly the same, so it doesn't really matter. I'm not trying to make you a programmer in any sense today. It takes a bit of time, and there's a lot of finicky stuff with every single platform. I'm just trying to teach you the basics and also how to improve your code and what the basic principles are, because it is quite different. The process of optimization and speeding this stuff up can be quite different from CPU code. So here's a GPU example. So in an NVIDIA GPU, you can run multiple kernels at the same time. Each kernel is going to be some sort of like function effectively. It's some function, some piece of code doing some processing. These kernels are actually grouped into grids, but not super important. These grids will have multiple blocks, and multiple blocks will have different threads. Anyone confused so far? Cool. By the way, if you have any questions, just raise your hand. I strongly prefer when people ask questions, because then I'll forget and be awkward. Here's a CUDA kernel. The simplest kernel you can. It's generally the hello world of GPU kernels. And it's just adding a vector. So this is sort of the example that we gave before. The global there means it's a kernel. It's something that runs in the GPU but can be called from the CPU. It doesn't return anything. Kernels don't return anything. And you pass in A, B, C, all of which are pointers. And if you don't know C, you can think of them as addresses or arrays if you know any programming. And then some number n. So A and B are your operands. These are what you're operating on. What you want to do is for each number, each index within your A and B, you want to add them up and then put that sum in C. So first, we figure out what the index should be. And CUDA defines these special variables called the block index and block dimension. But basically, this is just calculating what index you should be working on. And so your index is ID. And if your index is less than the length of your vector, you just take your C array, and then you assign A plus B. Super simple stuff.
Why do we need to check that?
You might have a vector size that's smaller than your block dimension times your
Why can your ID be greater?
It can be if you've made specific optimizations to try and get it to the right block size. So some block sizes are faster than others. This is also just a toy example that I copied off Oak Ridge National Laboratories.
I think CUDA has.
It does, but that's the example they had. So I copied it over, because I do not write that much CUDA. Here's an example I wrote. And I do not even know if this compiles. I'm pretty sure it does, but it's close enough. So first I defined two auxiliary functions. And the example is just counting how many points in a point cloud match some sort of filter. Totally weird example. It does not make much sense to do this. But that's what I've come up with, because I think it shows off some different features. So specifically, I make these auxiliary functions that take these float 4 points. So float 4 is a vector of 4 floating point numbers. So 4 decimal numbers, and then some max and min. Now I've put in comment here that each point cloud is 4 numbers because it's got an x, y, z, and then how bright it is. So when you get a LiDAR point, you'll get some sort of information of where this point is, and also how intense it is. You'll also get other values, but I'm ignoring them for now. And OpenCL defines this very weird syntax where you can do point.so2 and then give you all the indices from 0 to 2. So here I'm taking point SO2, which is the first three indices, x, y, z. I find the length of them. That gives me the distance of that point from the origin. And then I check that it's greater than minimum, and then I check it's smaller than maximum. If it is, I return true. Right? Very basic operation, just checking that the point is in between these two distances. You might want to do that, for example, if you're trying to figure out whether to apply some sort of operation. Maybe if you're too close, if the point is too close, you might be having points on the robot and you don't want to operate on those. If it's too far, maybe it doesn't really matter. You don't want to waste compute. The other one is just an intensity filter. We return true if the intensity is greater than some threshold. Yeah. And these are just auxiliary functions to make the code later a bit nicer, so you don't have these random conditions in between. The actual kernel is here, and OpenCL is very nice because your kernel is actually called kernels, not global, which is very weird. And the kernel is called count filtered point clouds. It takes as input this pointer to these points, and these pointers are global, so that means they live in the global memory. So they exist on the, if you've got an integrated GPU, you've got a RAM, things like that. And then it takes some threshold values, the intensity, maximum distance, minimum distance. And then this one's actually count output. So kernels can't return anything. So what you would actually do is you'd modify the count variable. Yeah. And here's the second part of this function. First, we get the global size. It gives us which index we should be operating on. And then we grab the point. So we've got these points. You just index them with the index variable, and you get your point. Very easy. Float 4, a vector of 4 points, in x, y, z intensity. You've got it right there. Then you figure out whether it's a good distance away. So you just call these auxiliary functions, filter distance, and then you also call filter intensity with the parameters passed in. And if the distance is good and the intensity is good, then I call this function. It's called the atomic increment function on count. And why do I do that? Well, as I said, you have all of these different threads operating at the same time. So for example, if I remember correctly, a lot of point clouds, when you've got a LiDAR sensor, generally you'll get somewhere between 10,000 to 40,000 points per second. Not per second, per iteration, per spin. So every say 1/20th of a second, you'll have to process these 10,000 clouds. So you'll actually launch. You'll tell the CPU to launch these 10,000, 20,000, 30,000 kernels, or like you launch this kernel with 20,000 threads, and it won't launch all of them at the same time. Your CPU is not that big, but you will have a bunch of threads running at the same time. And what happens if they all try to write to the same output? Well, they're going to be contesting each other and like fighting with each other. So programming languages will have built-in atomic operations, which sort of bring them in line, sort of make sure that they don't contest with each other, and you get actual usable output. Yeah. So you do an atomic increment on count variable, and then by the end of this kernel, when all of them spin, all of the threads have been run on all of the points, you'll have a count of how many points have a good distance and a good intensity according to your criteria. Any questions? Cool. Anyone disagree with my code here? No? Now, how do you write good GPU code, right? I gave you some pretty trivial examples, right? How do you make code that is fast, that takes advantage of your hardware? And there's like absolutely loads of principles. In fact, I could not begin to list all the things that you can possibly do. But I came up with what in my experience has been very good at speeding up a bunch of GPU code. And a lot of it boils down to memory, right? So memory transfer between your CPU and your device, whatever your device is slow. In fact, especially on a real-time device that needs to get work done, this is extremely slow. Now, if you're in a high-performance cluster, you've got a supercomputer beast, you're doing machine learning training, it doesn't matter if it takes a second to load up your data. But on a robot, when you need to get stuff done in a 20th of a second, this really matters. Right? So memory transfer is slow. So your first goal should be to reduce memory transfer. Don't transfer unnecessary data that you won't need. Use low precision if you can. So for example, if you've got a number that stays between 0 and 255, you can use an 8-bit there. You don't need it to be a 64-bit number storing so little data. You can reduce CPU and GPU transfer. So in a lot of situations, what you can actually do is you'll allocate a bunch of memory on your graphics card. And what you can do is you can transfer data initially there and then just keep your data there. You don't have to transfer it back to the CPU every time you want to get some output. Just give the output back. Don't write it back to the global memory or anything. Just keep it local. Keep it in the GPU. Yeah. You can also do early exits if you know that you aren't going to need to access some memory. So for example, what I could have done earlier is I could have checked whether or not the intensity value is good. And if it's not, I can just tell the kernel to stop, return. I don't need to get the float 4 value. Right? There's caveats to this, so I will get back to that. But if you know that you won't need this information early, just avoid getting it. There's no point getting that information if you don't need it. It's going to slow up your GPU. The next thing is efficient memory access, and this sort of relies on me having to explain sort of a finicky bit. But you want to have a memory access pattern that is contiguous where possible. What I mean by that is, at any point in time, you should try to access memory that comes one after another. And I'll explain why. So here's your sort of memory. Here's sort of your memory overlay, right? You've got the main memory, which is going to be your RAM. You've got your GPU memory, your GPU VRAM, and then you're going to have various levels of cache that are closer to each thread, right? So each thread will have a cache that's very close to it, and the further away you get, the slower it gets. But the way fetching memory between these banks works is that you've got something called a cache line, which is sort of a storage of whatever memory you grab. And so when you want, say, for example, that first address, it'll actually grab all of these 4 next addresses. There's a certain size, and it'll just grab a bunch of stuff that you don't need because it doesn't take any less time or any more time. So it grabs all of that at once. Now, if you've got a good memory access pattern, so for example, you're accessing those first 4 addresses at the same time, the red, yellow, I'm colorblind, so I don't know the other 2, bluish. And so if you're grabbing those first 4, it's actually going to grab all of them into this cache line here. And what's going to happen is all of the threads that are trying to get that data will just get it from the cache line. They don't need to go and get the next memory again. They can just get it from there. And if you've got this sort of efficient memory access pattern where you're just grabbing these 4 address chunks at once, it'll be extremely efficient. On the other hand, if your threads are designed in a way such that, for example, one of them accesses 0000, the other one accesses 0080, and so on, basically all of the red ones, what you'll actually have is it grabs the first 4 as the cache line, and then for the second thread, it actually has to get the next red one, which takes another memory access. And that just becomes extremely slow, right? And then you'll probably ask me, why the hell would I do that? Why would I get this sort of every xth value? There's no reason for me to do this in any realistic scenario. And I'll say, you might not mean to, but common programming patterns actually sort of force you to do that. So that's what my next point is about, making appropriate data structures. And so the most common one I want to talk about is this structure of arrays versus array of structures approach. Now, if you've got, say, a big point cloud, it's very, very natural for someone to make a class or a struct that consists of all of the information from that point, right? So you might make a class that has a x, y, z intensity or any other values that you might have, and that'll store all the data from one point in one contiguous array. You'll actually have a structure of these heterogeneous x, y, or x, y, z, intensity, etc., and you'll actually have them, one after another. And this feels very natural to us. It makes a lot of sense in terms of like good programming practices, encapsulation and all this stuff I don't really care about. But it's actually not good. And the reason for that is, for example, if you've got a thread working on that, for example, thresholding thing, right? What you'll actually have is like, you might have 16 threads or 64 threads at the same time trying to get the threshold. Now, if the threshold is actually stored as an array of structures in this approach, you might have XYZ intensity, XYZ intensity. And the memory access pattern that you'll have when all of the threads try to get the threshold information at the same time is to grab all of this in a very slow pattern, memory access pattern. It's much more preferable if you've got a structure that contains pointers to these arrays, and you pass the structure in, and then all of your threads will be grabbing these contiguous memory chunks, and that'll be much, much faster. It's actually incredible how big the difference is, and the issue there is just that memory access is extremely slow. Transferring data between memory banks is very slow. So biggest advice, reduce memory, good memory access. Again, along the same theme is shared memory. Now, what you might want to do is you want to have many threads operating on the same data. Now, if you can get your threads to cooperate and not waste their time getting data that they've already gotten before, that's actually much better for you, because you will have basically all of them cooperating and not having extra memory accesses. And I'll show you in what sort of situation this might happen is, for example, if you're trying to do moving average, right, or among other common operations, convolutions, matrix multiplication, variety of things, where you have this sort of input data, and you've got each output, which would generally have a thread of its own, has to access multiple of those. So here, it's a moving average of 3 inputs. It's totally feasible for it to be a lot more than that. You might want to have moving average of 16 or something like that. And that's extremely inefficient. Now, your compiler generally isn't smart enough to be able to figure out your memory access patterns very well. Very good chance it can't optimize this. But what you can do is actually you can make you can sort of group them into groups that share this data. So you might, for example, have 3 of these, right? And this one grabs that data, 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 and any extra that you can't grab if you have a special access for it. But effectively, what that happens is they all grab this data, put it into some shared memory, and that's shared between all of these different threads, and they have much faster access to it. They don't have to keep grabbing it from the global memory. You waste less time. Your threads are working together. And it's very common for you to try and optimize your group size and other variables to figure out the fastest way to do this, use local memory, things like that. A lot of the time, when you have GPU accelerated code, so for example, machine learning libraries, they will have extremely well optimized versions that use the right sizes and the right memory access patterns, and that's a lot of what they're optimizing for. And this one's fun. I find it very interesting, the way the fact that see, all of these branches, all of these threads are actually sharing this execution unit, and these threads always operate in tandem. But then this weird situations can happen where you've got some threads doing one thing and other threads doing other things. So for example, if you all grab a bunch of data and you've got a branch there, so an if statement or a while loop or a for loop, something like that, you might have what they call branch divergence. So all of these threads that are supposed to be operating in tandem are trying to do different things. And so what actually happens is the way the code is structured is for the threads that meet one branching pattern, they all operate in tandem, and all the other ones are doing nothing, absolutely nothing. They're just stalled, doing nothing. And then once that piece of code is done and the other ones are finished with the first part of the loop or first part of the if statement, is they get paused, and then the rest of the threads will start working in tandem. Right? And in this case, it's actually sort of trivial because it's a very it's probably not something you can really avoid here. But what might happen is if you've got situations where you've got a bunch of threads that are just waiting for other threads to get work done, that's wasted time on the GPU, it's wasted power, it's wasted energy. I myself have written code where there's like 90% of the threads are doing nothing, waiting for the last 10% to be done. And there's a few things you can do depending. You might be able to structure your code so that a lot of them finish early and can be returned. You might make smaller groups so that at any point you might have fewer groups, fewer threads in a group waiting, and the rest can be used as part of a different group, things like that. But it'll vary significantly depending on your situation. So yeah, just try to avoid branch divergence. If you've got a bunch of logic, try to figure out better ways of doing it. There's weird things like branchless programming you can do, or a variety of different things. But it's very dependent on what exact code you have. Take advantage of vectorization. So I told you about CPUs and how they have SIMD instructions, right? Specialized instructions to operate on a bunch of data at the same time. And GPUs do that, but like with steroids. So what you want to do is you want to hint to the GPU that it should be operating on a bunch of data at the same time in parallel. And I've got an example here using SYCL. So here you've got some. If your sum, input, ACK, source offset, etc. are float variables, so just single floating point numbers. What you might want to do is if you do the sum over these 4 floating point numbers, this might not get optimized. It might try to it might try to add these up in serial, so the first 0th index, first index, etc. But if they're stored as different types or casted to different types, like float 4s, which are vectors of floats, they might be parallelized, so they're not. So you don't have a bunch of serialization happening, and they'll just get pushed into the ALU at the same time, come out of the ALU at the same time. And I need to hurry up now because, well, actually I'm at the end anyway. More advanced tips that they sort of depend on what you're trying to do, but try to overlap your memory transfer and computation. Anytime you're waiting for memory to be transferred is time you could be using on computation, right? If you don't need the memory, if you need the memory at some later point in time, and you need to do computation in between, you can just do the computation while the memory is transferring, and then start working on the memory once it's done. You can, and this is a very fun one. I love doing that. The second part. Sometimes you've got fast algorithms, right, that do less compute, right, that need less compute. You might be able to swap out these fast algorithms for slower ones if they can be parallelized better on accelerated hardware. So it doesn't matter if you're doing 5 times the instruction if you can have 100 workers working away at it. It's very fun to do. Usually those algorithms are quite hard.
Can you give an example of that?
I cannot because it's NDA'd, but There's some really fun stuff. If you look up, most things have parallelized algorithms. People are working on them for some reason. There's a whole class of researchers whose entire job is, I will take this random algorithm today and I'll try to speed it up like 100 times. And it's a very fun thing. You should try to look for, if you got something that takes a lot of time and you don't know how to parallelize it, look up research papers. Almost certainly someone's tried it and has a better approach than you could have thought of. It is the leap between parallelizing something that doesn't look like it can be parallelized. It can be quite mind-boggling. So yeah, last one, specialize for your own hardware. Now, I personally don't believe it's actually that important to do. I think people tend to exaggerate how important specializing for your, fine-tuning for your own hardware is. Most of the techniques I've mentioned today will work on basically any piece of hardware. It doesn't even have to necessarily be a GPU. A lot of the time, FPGAs and stuff will benefit from the same techniques. But if you do really need to squeeze out that last bit of power and you've got a bunch of time to spend on it, you can actually do that. You can fine-tune what your group sizes are and what exact operations you use. And most hardware manufacturers offer special libraries that have extremely fast implementation that they've had their people that actually know how hardware works work on them. And those are some advanced tips. Now, fun thing, an integrated GPU. So if you've got an Intel graphics card or something, you might, or if you've got an Intel CPU or something, you might have seen Intel HD graphics or UHD graphics. Or you might have even seen Intel Iris graphics. And those are integrated graphics cards inside your CPU. What's different about them is they actually they don't have a memory of their own. They sort of share the same memory as your CPU. And it's actually really cool because what you can do is you can avoid some of the memory transfer burden that you would generally have. And so you can just store the memory on your RAM, operate on, get that as memory from RAM directly without transferring it over to some discrete graphics card memory. But there is risks there. So if you've got an integrated graphics card using a bunch of memory, it actually uses the same memory bus. And what that means, and I know people who this has happened to, is that because the GPU is using all of this memory operating on so much data at once, more than the CPU could ever handle, the memory bus is saturated. It literally can't transfer more memory. And the CPU, all the processes on the CPU that are pretty important for a robot or something, otherwise the robot will crash generally, are literally just waiting around to be able to have access to the memory that they want again, which is weird. And any sort of optimization you ever do, doesn't matter whether it's hardware acceleration, software optimization, profiling should be your first step. No matter how smart you are, modern computer hardware is so extremely advanced, it is very, very hard to predict how it's actually working. And the only way to optimize is figure out what's taking time and then optimize that. Don't waste your time working on stuff that might be optimized already. Use profiles to guide your knowledge. And it's getting late now, but it's mostly just a couple of slides left. One option for NVIDIA users is the NVIDIA profiler. So these profilers will actually give you, basically, they'll tell you what's happening when, what kernels are running when, how long they take, what different functions might be called. Intel also has one. It's called vTune. I quite like it. It's got some fun detail there. So it can tell you how much memory is being used. So you'll know whether or not you're saturating your memory bus. You can see how many execution units are stalled. So if you've got threads that are being stalled because they're waiting on other threads to finish or something like that, you'll be able to see it there. You'll be able to see what tasks are running when. You can see the example on HD graphics, so that's on an integrated graphics card. Now, you've seen a bunch of me use, I think I had examples from 3 different frameworks. There's a bunch more. AMD's one is obviously very close to CUDA, but it is quite fragmented. And it's not totally obvious how you would integrate the system into an actual robot. Good news for us is actually there's people working on the problem. So the latest version of ROS, ROS is the framework that you'd be used to or will learn if you do the robotics subject at UQ 4202. The newest version of ROS, ROS 2, has a working group, just a bunch of people and a separate company working on the problem of how do you make a generalized architecture such that you can use GPUs and hardware accelerators in a more general way. So they've done some pretty cool work in coming up with ideas of how to integrate it into ROS. But for now, until that's ready, the best you can do is figure out what GPU you use, what works for you, pick what you actually want to use, whether you want to give yourself up to a walled garden like CUDA, or whether you want a more open approach so you can switch between different hardware. There's benefits to both approaches. In fact, you can actually go more specific than that. You can even use Apple's Metal to speed up using the Mac GPUs, which are incredible. And there's benefits to both approaches, sort of really up to you. And with that, that's the end of my talk. I don't think I have any more slides, so cool. There is food outside. I'm also outside if anyone wants to ask questions.
Yeah, thank you for giving that speech, and not at all inspired by any club's traditions.
You've got mugs.
We do have our Mars mugs.
So cool.
Our president. So there is the first one to be given out.
So many mugs now.
Thank you, and yeah, we'll have pizza set up just outside once we're finished in here. So thanks for turning up. Great to see we've got a good bit of a crowd. And yes, thanks guys.
I'm also open to talking about working in robotics or anything. It doesn't have to be about hardware acceleration or anything. Did the live stream work? Did you have any issues with the live stream?
Well, besides the thing, it was fine.
Cool.
He was going through that.
Cool.
AKLM commented.
Nice.